Suppose I have a really big capacitor right here, some capacitance. And then I know that this is going to be equal to whatever the charge is stored on the plates over delta V. And the delta V, let's throw a power supply in there. So whatever the potential gain is here, I'm going to lose that much potential. This will be the positive and negative sides of the capacitor. And now I've changed the configuration. I still have the same plates. All I do is I just now have two wires hooked to the same power supply. There shouldn't be any difference. I mean, just as much charge, just that when the electron gets to here, it's going to go one way or the other, but it's still going to end up on the plate. Whether it just goes straight or splits, it really doesn't matter. So the capacitance is still Q over delta V, where this Q is the magnitude of the charge that's on the positive plate. Now I take this and I configure it one step more. I take this two plates. I have the exact same size of plates, except I put a little gap in here. So basically it's like I'm cutting the two plates. I still have the two wires hooked to it, hooked to the battery. It's still going to hold just as much charge. For the exact same potential, it holds just as much charge. Except now I officially have two capacitors. So this would be C1 and C2. And so the capacitance, the original capacitance, we'll call this total capacitance, is just going to be C1 plus C2. It's just the sum of the two capacitors. So for capacitors in parallel, so capacitors, it's worth writing out, in parallel, the total capacitance is just equal to the sum of all the individual capacitors. So just a quick and dirty, I have a capacitor here, I have a 5 farad capacitor here, I have a 4 farad capacitor here, and it's hooked to a 12-volt battery. Then the total capacitance is 9 farads. So this is known as the, I said total, equivalent capacitance. So instead of writing total here, let's write C sub EQ for equivalence. So this would be like having a 9 farad capacitor and a 12-volt battery. I can now find the charge on the plates. I know that C is equal to Q over delta V. So that's 9 farads is equal to Q over 12 volts. And so the charge on the positive plate will be 12 times 9, which is 108 coulombs, or volt farads. So I would have a total of 108 coulombs of charge, but it's split between these two, and we can find that also. If I do a voltage loop here, if I gain 12 volts here, I'm going to lose 12 volts going there. If I gain 12 here, I'm going to lose 12 going there. And so it should be able to split the charge on for this plate right here. I will have 4 is equal to Q over 12. Here I'll have 5 is equal to Q over 12. And so the charge from this plate will be 60 coulombs. The charge from this plate will be 48 coulombs. And on the negative plate, negative 60 coulombs and negative 48 coulombs. And by the way, just as a safety note, don't ever get in near anything that has a 60 coulomb charge sitting on it. That will kill you. But anyway, the whole point of this was adding capacitors in parallel. Now, let's talk about series. If I have my power supply here, a 12-volt DC power supply, and I have a capacitor here and a capacitor here. So the question is, this is capacitance 1, capacitance 2. What is the total capacitance? Well, think about that. When I hook the connection up, I have electrons leaving here. So I have electrons traveling this way. Current is traveling the other direction. The electrons are traveling this way. An electron lands on this plate, driving an electron off of this plate, leaving a positive charge behind. And so this gets a negative charge, driving another negative charge off that plate, leaving a positive charge. So whatever charge I end up here, I'm going to end up, so if this is negative Q here, I'll end up with Q here, negative Q here, Q here. In essence, all I've done is I'm still just storing some charge Q. I know capacitance is equal to Q over delta V. I have some voltage drop here and some voltage drop there. So we'll call this delta V1 and delta V2. I know 12 minus delta V1 minus delta V2 is equal to 0, because whatever I gain I have to lose when I get back to here. So delta V is Q over C, so this becomes 12 is equal to Q over C1 plus, just bringing those over also, plus Q over C2, which is Q times 1 over C1 plus 1 over C2. I know the voltage here for the equivalent capacitance. In other words, when I say equivalent capacitance, if I took those two out and replaced it with a single capacitor, what would that capacitance be here? This is known as the equivalent capacitance. And I have some, well, stick with 12 volts. It can be anything I want it to be. So for this scenario right here, I know that 12 volts, since we've established, is going to be Q over the equivalent capacitance. So this has to be equal to Q times 1 over the equivalent capacitance. In other words, for capacitors in series, and that's worth writing out, one over the equivalent capacitance is equal to the sum of 1 over C sub I. I goes from 1 to n. In other words, 1 over C1 plus 1 over C2 and so forth. Now I did it with just 2 capacitors here. It works with 3. And just as over here, I did it with just 2 capacitors, but it works for however many I have in parallel. Just do a quick example here. I have, again, a 12 volt battery. I have a 5 farad capacitor, and I have a 4 farad capacitor. What is the equivalent capacitance? Well, 1/5 plus 1/4 is equal to 1 over the equivalent capacitance. Pull out the handy dandy calculator, and I don't know if you'll be able to see the numbers there, but there are numbers there. Let's hold it up so you get a little bit better light. So 5 inverse, 4 inverse plus, and then inverse that. So I get an equivalent capacitance of 2.22 farads. Now, I recommend that you try this at home, making sure that you understand it. Probably the biggest mistake I see is people get to adding these two, and then they forget to do the reciprocal at the very end. Because when I add these two together, I get 0.45. That's equal to 1 over the equivalent capacitance. And so the equivalent capacitance is 1 over 0.45. The other big mistake that students make is they confuse parallel and series. Again, this is parallel, and this is series. Now, one way of telling the difference is there cannot be a junction between them in series. So any charge that is leaving this plate has to go onto this plate. As opposed to here, any charge that's leaving this plate right here will come to a divide here and actually will split. Or if you think in terms of current, current is flowing this way. When current gets to here, it's going to cause current to flow to here, cause current to flow to here. There's only one path. So series, there's basically one path from component to component. Here I have 2 paths. There's a junction in between. Another way of doing it, as we get into, especially in the next chapter, presumably, is that for parallel will have same voltage. Series will have same current.